see. You would just see random addresses. Bob says that there are some rules that you can use to figure out, probably without otherwise looking it up in a table or asking someone, what types of machines these are. So maybe you can tell us 08001B, those are all data general boards, right? That's what that means. That's the manufacturer ID of 08001B. In fact, it's useful to know what those things are. It's one of the things we're sort of planning to do in future versions of Sniffer is automatically at least have a list of known manufacturers. Fairly quickly, you tend to recognize 3Com, Unger Bass, some of the, Sun, and DEC. You say, oh, look, there's a 3Com station, there's a DEC station. The first 6 characters are the manufacturer ID. What is supposed to be? In fact, if you see something really weird, that also is not it. The next 6 digits are a serial number. And do you want to tell us a little bit about the structure of that serial number for DG?
Yeah, we found out that the next 2 digits, 04 and 06 in this case, tell us whether we've got through 4. I happen to know this was my historic warrant. And we decided it was 04. I believe 04 was the PLC, 06 was LLC. May have been the other way around or not. That will give you and he took the other table names. The other table handy?
This system doesn't. Warehouse laws?
Yeah.
Is the on that really fast board, source data general summary. They go with data general, IG, or under the fast.
Data general. Since I know I had 2 MVs and PC on the system, I have to know 04 must be the LLC, 06 must be the PLC.
Okay. So let's do this. So let's just take right here.
Just be like you, so
what it's done is we'll play back this data, so it won't have to. And the system has accumulated a list of DLC or hardware addresses, means data link control, physical addresses, and it's seen some of which had names in a table. Here's the one we typed in before, no one. And notice these addresses right now, so we play it back, simulation, they don't have symbolic names. So we can just manually type in symbolic names. Okay, so let's give that a name. Okay, let's call that, say, Bob Server. And these other things here are workstations. So let's pick one. And let's say I was working on one of those. Okay, so these things are in my list of names now. And I'll hit escape. At this point, there are several things I can do. Probably a reasonable thing at this point is to save names. Okay, so I go down, hit the N key, and hit enter. And now it's just writing that little table back out to this. The next time I reboot the station, it will have those names in this table. And remember them until I delete them or otherwise edit them. So let's just go back now and replay exactly that same data. See what happens. And now here, you see it's using the names that we use rather than the symbolic addresses. And if we went through this process and if we had identified and given symbolic names to all these stations, then generally you see name on the screen. And anytime you see an address in hex like this, it's a sign of, what is that? Again, why is that station? Is it a new card? Is it a bad board? Something like that. So generally, we do that. Let's do another thing. Now that we've sort of set up this name, and it's a good time, let's just see, let's go back to our capture filter. Let's see how busy Bob Server is. Okay? So we can go back now to my filters. I'm going to go up to the capture filters, and I'm going to go to my station address list, and I'm going to say, gee, I only want to see traffic to and from Bob Server. So I go to this point, I hit enter, it again shows me a list of names sorted and alphabetized. I press the letter B, hit enter. Now it's going to collect data from Bob's server to a station. And because this check mark is on here, we'll also record stuff to Bob's server from the station. That's the thing that's supposed to do. We're going to see how much activity Bob is doing with Bob and B is on the network. Now we play back. Okay, you see here, these counts are different. Here we're getting 88 counts, 44, whatever. Okay, 141 were on the network. Only 57 apparently were the use of Bob's server, and Bob's server is talking to Harry, he's talking to something, close to low. Which user is making most use of Bob's server? Harry. So that's sort of how we can very quickly, using the screen counters, get an idea of network activity, who's using the network the most, and so on. At the moment, those particular frames, those particular counts are just counts. How many frames? Well, there were some big frames and there were some small frames. One of the options, I would press F6, one of the options that we had, instead of showing the counts of frames, is I can show kilobytes to the counters. Then it will add 1 or 2 or 3 kilobytes, bytes, rounds of kilobytes, or I can show it in terms of percentage of amplitude. Alternatively, in a large network, there's one other option, which I won't show you now. Instead of seeing these pairs, counter pairs, source destination, you can just see source. So individual count. So show me the data tabulated by source address. My 50, 100 stations on the network. The first thing I might like to do is just the source address. And very quickly in doing that, you can tell, it's another way to tell who the servers are. Servers stand out, obviously. The other guys won't count as the crazy. And then the other guys distributed around, generally speaking. If things were normal. I guess one of the things that I think is incredibly powerful about this kind of system is that you can get a huge amount of information about how well the network is working, whether it's reasonable, whether or not something seems broken, just by looking at the screen and playing around the output. We have to go through one piece of protocol, we have to go through one packet. People, system engineers, system managers learn very quickly how their network operates and what the usual traffic patterns are, what looks right. And the same thing we'll see in a bit perhaps at a detail level. You know what a normal PCI session looks like, what the normal acknowledgments and so on. But I would say that this kind of activity is like in the old days when computers used to have console lights, and people would literally go in and say, oh, it's in a loop, very queues or stuff. And literally, they could tell it's in a loop and what loop it's in by looking at the pattern of lights. Same thing here. And I really think the people in the field ought to be encouraged and will be able to, at this level, take something like this, unplug it, hook it onto the network, just press capture, and look at the counters, and start to get a clue of the magnitude of the problem, of the nature of the problem, to at least know where to start looking at. For instance, someone goes into their office one morning, a large facility, turn on their workstation, it's taking forever to boot up, it's trying to access some files in the system. It normally takes 30 seconds, 5 minutes gone by. It's not dead. You can see things like, the whole network is running slow. There's basically very little activity. Everything is running much slower than it is. I better look at collisions. I better look at odd frames. Maybe there's a bad cable somewhere. It's global. The whole network is bad. Or you only see part of the network. You could see that only some of the stations are there. There's apparently something really bad happening in some other segment, some station IDs that normally you see 150 stations, you only see 25 addresses. Okay, part of the network is okay, part of the network is not okay. Or you start to see, one server, is booming along. He's going just like he did yesterday. This other one is limping. Okay, it's probably not the network. It's probably something about that particular server, but the server is not down. Okay. Alternatively, you see, gee, everything's fine. The network is not busy. In fact, it's never looked healthier. It's chugging along, 300 frames per second. The servers are clicking over. Hey, nothing wrong, right? Then you say, wait a minute, let's look at that particular server, my Bob server. Let's look at the clients and you find out that old Harry here is using up 90% of the bandwidth. I mean, he's just sucking juice out of that server like crazy. He's playing games or whatever he's doing. The network is working. It's just that this guy, who generally is, the CEO of a company or something, can't get on the system. But it's working. This is an administrative problem. Actually, it's not a technical problem. It's nothing broken. It's just that, realistically, there is nothing in a network that prevents a user totally inadvertently doing something on his desktop which gives him an unfair advantage and sucks for most of the resource out of the system. That's an administrative problem. The engineer is not going to fix it. They get an opportunity to sell, or salesman to come in and sell a big server. But you ain't going to fix it otherwise. And those kind of things actually are very weird, and they just happen randomly. Best of intentions. It doesn't take anything as humorous as I said, playing games or sorting your phone book. Quite inadvertently, you can use a word processing package day in and day out, and it's fine. And one particular day, you get to the point where you're suddenly editing a 10-page document instead of a 5-page document, and it decides it's going to page in and out over the network, using the network server disk as a scrap disk, and it pages like crazy. It does a great job for you. Everyone else is at their knees. Nothing's happening, but it's working. It's working as specified according to the book, no problem. And once you identify that, someone will fix the problem. It may not be that field person. Okay? But someone can now say, yes, that word processor, here's how you can put your temporary disk file on your local hard disk. Or use this word processor. Or edit your document in 2 parts. Change this batch file. Another example of that is a very typical thing that happens in a user-oriented type problem that can absolutely kill a network. It's very easy to set up a very complex search paths for DOS to find files. Look in this directory, look in this directory, look in this directory. And it's trivial to set that up, and it'll always be there. It's a real aid. However, something like that, if abused, I would say, if used inappropriately, you can end up systematically doing it in the worst possible way, so it has to look through 20 different locations before it finally finds the file. And it will find the file. So the user doesn't notice the problem, but he's causing 20 file searches to happen. He's discovered this great feature, he's told everyone else in the building about it, so everyone's using this, they're real happy. Meanwhile, the poor server spent all this time doing directory lookups, and it's a threshold effect. It has just enough memory. I don't know the implementation of the MV servers, but I assume they're like any other thing. Given a certain amount of directory lookups, a certain amount of memory space, they can handle it real efficiently. But then he asks for, one too many, suddenly they start thrashing, just like the paging example, and things suddenly fall on the left. Okay? And it was perfectly acceptable for that user to search 19 directories. When he did 20 and everyone else in the building started doing 20, response time just goes to 0. Infinity. Response time goes to 20 seconds, but it works. And a trivial change, swapping, modifying one little batch file, can change response time from 20 seconds back down to 2 seconds. And that's it. I think those are really going to be very difficult problems. I don't think all the real complicated problems, will be there. There will be them. Certainly in the initial parts of the project deployment, there will be real hardcore bugs. And it's going to be frustrating to find real hardcore bugs where, hey, the protocol's just not working. It's really sending the wrong packet. It's really getting out of sync. It's really, real trouble. Those will eventually disappear and get withered out of the system, and then the only problems really going to be these configuration kind of issues. But you can't tell them from hardcore problems.
Do you anticipate that just about every network manager will have one of these, or a large set of networks? That's what you're hoping, I'm sure.
Yeah, right. You answered the question.
Based on your experience in the past.
For a large-scale network, I would say that probably in a large-scale network, looking at the financial investment that someone has and the frequency that miscellaneous user problems happen, it's probably recommended that that's a wise investment. We're not looking at a major commitment compared to the size of the network. And it's just sort of like insurance. I mean, if you don't have this kind of product, you're referring to like an end user themselves, owning one or having one, as opposed to fire drill time. Then you have to ask what's the cost of fire drill. Everything's fine. 5 o'clock in the afternoon, suddenly you can't print the checks. Someone will come in, the serviceman will have this tool. Maybe you won't come in Friday afternoon. Maybe it's got to be blown from Westboro to put up. And then, the man put up will come in and plug it on the network. And, okay, the problem will be solved by 2 o'clock Monday afternoon, which is incredibly fast compared to dark ages. But he may or may not, wish to look at some of those things himself. And I guess what we're making here is, I think I can stop the presentation here and say this is very valuable. Very, very valuable. It will solve a lot of the kind of issues very quickly in the field. And I want to really emphasize that. Developers need to go on. It's another reason to develop. Although the developer needs to know, hey, look, I type login. Did or didn't the packet go here in the host? Nothing came up on my screen, and just seeing a count 1 up there is incredibly valuable. But that's more the exception than the rule. This kind of philosophy, I find, is to help people, not go off and solve the world problem. We spend a lot of time chasing down all kinds of things that generically sound the same. Just a little bit of brains can help figure out where to look and where not to look. One of the things that we are looking at would be to automate some of those decision making. It would be nice to have the system be a little more self-aware and say, gee, this server normally at this time of day sends 100 packets per second. It's only sending 25 packets per second. That's weird. Look into it. Or why is it sending 500 packets per second? That's a much harder problem. And I guess we are counting on human intelligence and not artificial intelligence to be able to look at those screens and get some feeling for what's useful and what's not. Certainly, I was talking to Lane, and you might share your experiences at the presentation in New York.
Basically, we had several hooked up to the GCI demo area, and just by looking at the screens, we had this set up. We had the names of all the different demo areas. We could tell who was demoing, who wasn't, what systems were open, and with the clicker especially, you get very, very used to, what are you doing, what are the demos, and you could generally tell if things were normal enough, just with a quick glance, or you could hear it across the room, or all of a sudden you hear a loud noise. It's like, something's going on, and go check it out, see which PC is having problems or whatever. But during the demos, we found it to be very, very useful, just as a tool, just to see what was wrong.
At WeekV, I've had over 5 years experience with this kind of tool, and it's just incredible how much detail you can get out of such a gross look at a network. People can actually see server saturating, and you can tell, there goes the print server, someone's running off with a document down there. You can very quickly get to know the pattern and the counts and so on, and what's going on, and it's useful. Both servers and person and so on. Let me suggest I'd like to stop now. Rather than go on to the detailed displays, let's take a break. It's noon. All right. Try to give sort of a basic overview of the Sniffer, the data flow, how most of things. There's one kind of filter to talk about, address filter to talk a little bit about good package net packets. The next thing I wanted to say a few words about are protocols, how you can filter various protocols. So just to get some common ground, let me give a thumbnail view of how the Sniffer thinks about network products. And a typical example we just use here, for instance, is the, let's say, PCI. And whether it's running on an Ethernet system or it might be running on Shoreline, the picture of the software protocol is pretty much the same. I assume that many of you have seen the general descriptions of layer protocols. Basically, we have a series of layers of software logically communicating, and in our notation, we refer to the lowest level of protocol as the data link. control, which basically relates to the specific frame formatting or packet formatting that's being used in the network. So issues about source and destination addresses, broadcast, multicast, things like that. Checksums are all in the domain of data link. And data link's job is quite simple. Data link talks to data link and basically just deals with hardware address and says, hey, here's a packet, good luck. There's no idea what the packet is particularly, it's just responsible for getting it there. So generally the initial portion of the packet has information about the destination, the source, maybe some bits associated with broadcasting, checksums on there. I'll mention that in the case of, not in the case of Ethernet or Starlink, but in the case of some other network, for instance, there actually is another type of physical packet that may be your own network. And that is called a MAC, media access control. Packet. And this is actually also a data packet. It has source and destination addresses. It is used for error reporting, certain kind of network management features. You turn on a station, wants to boot, and find a server that can boot it. Generally, media access control is used for some of those issues, and then eventually the data link is used to do real data. That's not the case in the case of Ethernet or Starlink that we're just talking about. Data packets, normally is one class of data packets. Okay, so there's a set of rules and regulations about how data link talks to itself. There's another piece of software that then lives on top of data link, which is called logical link control. And logical link control is responsible for seeing that the packet gets to the right particular sub-process, the right particular subsystem, deals with, for example, a certain level of sequencing and acknowledgments among these packets rather than the way they get there. So similarly, the logical link control has a protocol, has a way of doing business, has a certain set of formats that are legal, and that information is typically represented by several more bytes in the packet. So the next few bytes deal with the information content of logical link control. And the wonderful thing about all these layers is that you may have the same logical link control running over different Ethernet, StarLink, tin cans, X25, chewing gum, and it doesn't care what's below it. Right? It says, well, I know how to talk to another copy of logical link over there, work by some other vendor. I don't really care what's performing the packet. I just know these bits, legal bits, that's what it should be. Similarly, he doesn't care what the data is that logical link is carrying. So whatever it is that's after logical link, or before logical link also is irrelevant. He's got his own protocol, he's got his own peer-to-peer communication. A slight diversion here is in the case of Ethernet. In the case of the 10 megabit-based technology, there actually are two different formats of packets, starting with this logical link control, starting with after the destination source addresses. And the sniffer recognizes both of them and treats them, interprets the data somewhat differently. In general, in almost every network situation, it's usually the case that there's some bit, some byte, some control field, which tells you how to interpret the data. In the case of Ethernet, what's involved is essentially incompatibility. And if you look at the next 2 bytes of information, there are really 2 ways that information can be used. You're totally incompatible, inconsistent. There's no way to tell it except context. One of those is what we call an Ethernet. The other one we'll call an 802.3 network. And at this point, what we're referring to has to do with the software that's running on those 2 different styles of network, not issues related to details of cabling and so on. Basically, in an Ethernet, those 2 bytes and here are defined as a field called ether type. Okay, and ether type fields are numbers, originally I believe by Xerox, something like that. which then gave the protocol the nature of the software that was followed. For example, TCP/IP, all packets that begin with 0800 are IP packets. We must have that. Things that are using XNS protocols have 0600. Okay, and there are a handful, there are a couple dozen of those that are Then there's another style of network, which is an 802.3 network, which carries official IEEE 802.2 modular link controller. Again, per some specification. In that case, these 2 bytes are always a link. They're a small number which has to do with the length of the data that's being carried. Nothing to do with the software, and it doesn't tell you what's coming, just a link to it. And then they continue to converge. So Ethernet goes that way, the 802.2 networks go this way. There's no way to tell them apart except look at the data and look at the field. It tells you what it probably is. And actually, there actually are quite a few operational networks in which these 2 styles are mixed on the same cable. And there can be some curious effects. If, for example, on an 802.3 style network, the station happens to send in a packet that has a link that looks like an Ethernet type, Ether type, vice versa. It turns out, in general, with a few special exceptions, the values for ether types, the values for lengths are not supposed to intersect. So that if it's a small number, it's probably length. If it's a big number, it's an Ethernet type. Except where that's not true. So there are times, at places where suddenly you may get some strange phenomena that might be attributable to that we will, in our conversation today here, just talk mostly about 802.2 networks, although TCP/IP falls in a different category. The principles are all the same. And the sniffer basically looks at the data it's analyzing and makes a judgment as to what it thinks the nature of the data is on a target network-wide basis, and you can override it and change it. So in the case of the 802.2 network, there's this particular 802.3 network, such as PCI. There's then this 802.2 protocol, which is specified in a book, and certain patterns are legal and certain ones aren't. And the system knows that. It knows the rules of 802.2 according to the Bible, the tablets that Moses put down in New York and Jubilee office. And if it sees data that looks like 802.2, sort of almost, but isn't quite, then it will put up question marks and various other kinds of messages saying, this doesn't look quite legal.
It actually doesn't look and make that kind of decision.
Right.
It doesn't send it up based on. I didn't know that interpretation was made.
Yeah, it makes interpretation, and in fact, everything must be, strictly follows patterns. And I'll give you an example of where that doesn't work, where there are proprietary extensions that are made, or things that stray from the standard allowances would have to be made for that kind of behavior. An example of that is on Ethernet. If you look at XTS, Zodiac actually uses some bit pattern, some combination of the control fields here in 802.2 that are not according to the Bible, that are DG extensions. Well, in other cases, you find things that are not so much extensions, but vendors tend to be ahead of standard. So they're proposing something, it's going to be accepted, but it's not yet officially blessed, but everyone's doing it. So we often see that kind of thing. And it will say, unknown command. That sort of message will come out. Okay? And then when that happens, of course, it doesn't know how to proceed. It basically says, okay, it looks like 802.2, but it's unknown command. It doesn't really know how to proceed, so it stops there. And then maybe lots of data following it, it can't make a stand for what that data is.
But Sniffer, can you see things like XX?
Yeah.
Right.
Heartbeat? Yeah. Now we get up to the next level. Above this is that the logical link control contains, for instance, this is typical at all these levels, we really have very often two, almost every level, I think it's sort of a fork in the road. You either have a data packet at that level or just an acknowledgement at the road. Acknowledgement basically says, okay, I acknowledge whatever data it was you sent me or whatever's going on, something, that's the end of the story. Okay? On the other hand, it could be a data packet at that level. In which case, for example, logical link might have an ACK or it might have a logical link data packet. If it's a logical link data packet, in the case of PCI, then it's an ISO network style message that then follows in that data packet. Okay, so if it's of the subclass data generically, then it ought to have ISO network type BitFields. And there we see, here's the first time we're introducing the concept of internetworking. Generally you're familiar with that, but here the actual entity address, the NSAP address, will be found, not the physical link address. In fact, this permits us to do analysis based on that address. We have backbones, we have bridges, and actually tell us that I just want to look at traffic from this entity to that entity, even though it's being routed over the bridges. And ISO network also has its rules and its interpretation. Not every legal combination of its devices is legal ISO, and again, we'll show you the fields that know the benefit. Something is illegal or reserved to other identification. ISO network in general then will carry the next level of protocol, which is transport. And here's an area where we definitely know there are changes being made. These things are not moving, are not still the standards themselves are draft standards. They are being revised, they are being extended. There are extensions being made by DG and others that are somehow built in. These things attempt to track reality rather than theory. This is routing information. And then here we have basically transport or sequencing of packets, the sequence numbers, and various connections get set up. This may or may not be the place, maybe another level, which has to do with setting up connections, some kind of session type protocol. And eventually we get to an application protocol, and one in particular that we'll deal with is SMB, which stands for Server Message Block. And SMB talk is DOS talk. Okay? That's the Microsoft DOS or compatible implementations, sending messages like, hi, open this file. No, I can't open this file. Try and open this file. Read this record, log this record. There's, several hundred messages that they can send back and forth. And again, that's represented ultimately by some data stream out here in the packet contains, let's say, the SMB portion of the message. Now, the sniffer's view of the world is that it knows about things like SMBs. It knows about them abstractly, whether they're being carried by ISO protocols in the case of PCI, whether they're being carried by XNS protocols in the case of pre-nominal VAS, whether they're being carried by IBM's NetBIOS in the case of IBM's PCI program. That's really irrelevant, and if you look at a particular operation, if you sit down at a PC and type directory list, generally speaking, the content of the SMB message will be identical. And totally independent of how it gets there, where, and so on, and vice versa. It doesn't know what particular application is running, what data is passing. There's no higher level interpretation of the data that it's reading and writing in its files. Some of the things that we saw yesterday, for example, are that if you do a DOS-like application, it generates messages of all these different levels. Right? Each one has its own rules and handshakes, ACKs, NACKs, transport, sequence, switch numbers, SMBs, and at each level of this protocol, we can look at that level independent of everything above it, independent below it. We take a horizontal slice, and we can see that that level is acting reasonably. That it's not, for example, saying the same packet over again twice. It's not re-acknowledging a packet that it shouldn't. Okay? And this is an area with a lot of performance, a lot of room for making performance errors in the sense of perfectly correct implementation, but one that is relatively inefficient. Classic examples of this kind of thing would form a category of like redundant acknowledgments. For some reason, the system sends out too many acknowledgments, either duplicates an acknowledgment, or it's what I call an over-eager actor. The over-eager actor sends out one acknowledgment immediately when he gets the data, and then some other slight parameter changes, and he sends another acknowledgment with a slight parameter change, and then another one, and it ends up, in a very short period of time, sending out multiple acknowledgments. And if you only had delayed slightly, that should have piggybacked all this information in one packet. Was that good news? Those kind of problems? Was that bad news? It will depend again very much on the life of the product, where a product is in its life cycle, and the usage of the system, and so on. Initially, on a very high bandwidth environment like an Ethernet with very low utilization, who knows? Who cares? That's irrelevant. Given Starland, heavily loaded system, lots of gateways, life and death can occur based on the fact that you send a few extra acknowledgments here and there can totally saturate gateways and bridges and other kinds of products, causing extreme havoc to other people sharing that same facility, which is what makes it particularly complicated. And again, you can be on a particular PC, particular workstation, running implementation of Telnet or something like that, and that particular one, which might not be part even of the DG offering, but simply sharing the same cable plan, might generate traffic to a particular gateway or something that causes it to have some very performance problems. Those are more sophisticated things. Those are not the kind of things that you expect to be picked up by an on-site field engineer, specialist, visual person, managed support person. We have to get involved in that. Those are the issues that ultimately perhaps developers would have to look at, or installation specialists to control those things and understand those things. And the Sniffer has the capability of doing that. One of the things, though, that we believe is that lots of problems are going to be really application-level problems, things that you would see by looking first at the application level. Now, what the application level is depends somewhat on the application. Okay, if we're doing DOS stuff, that's great. It's an SMB. And we were looking yesterday at some CEO WS, and what happens is the system, yes, it understands PCI, it sees all these different layers, and then when it comes to the point where the transport layer is moving the data, it says, well, that's data. It's not the data that the sniffer knows about today. Okay, it shows it to you, it's in text, you can clearly find just those bytes, it knows everything up to here, and then it says, gee whiz, there are 12 bytes here, 500 bytes. That shows him and asking him. This is very helpful. It would be more helpful if it knew, this byte means, open a file, read a reference, whatever they are, and that's something that could be done. The General does it, DG does it, in various ways we can go. They give out to you these handouts. This is a manual for the system. Three different pieces. That is the basic manual for the token ring version. One more. That is an addendum to that original manual, which describes some other features. And basically, those two in conjunction describe a token ring product. The Ethernet product is the same in the interim as the Ethernet manual is redone. Apart from those features, there is this simple overview which describes how the Ethernet product slightly varies, like it has collisions and things like that. But I wanted to point out to you, if you look at the addendum, I can have one in a second, and open it up right to the center, page 179, it says Appendix C, Extending Sniffer Protocol Interpreters. Okay? And this is what we're talking about here. And there's a lot of technical details here, but I'll give you your phone forward to page 196 and 197. 196 is sort of the statement of a problem. It says, imagine that you have a protocol with this on SAT number 44. That's one of these ISO type demultiplex fields down in logical link control, and that protocol has the formats that we described here. There's a 1 byte something and a 1 byte something and a string and so on. All right? And you would like to have the system interpret those protocols. The program on the right-hand page is the complete text necessary to interpret it. I guess we're sort of running ahead of ourselves because I haven't shown you the examples of what it is that we mean by interpret. But basically, that's to decode the fields, show them to you, okay, indicate the values. And the amount of work it takes to handle a simple protocol can be very simple. The amount of work it takes for a complicated protocol can be, literally tens of thousands, 50,000 lines to do, SNA implementation. To do a little bit of protocol, which by a little bit I mean, for example, simply recognizing a major verb, the main field, the main opcode field, and decoding that into English, you can see, open, close, read, write, or whatever, connect, disconnect, look up. Okay, it's basically starting with that program on the right, which is part of the Sniffer system, and hacking away until it decodes your particular fields. And in general, what a protocol interpreter is a piece of code that ultimately gets called by all these other portions of the system as they're interpreting their fields. At a certain point, it says, gee whiz, transport is done. It says, I have some data left over. It's user data. I wonder if that's an SMB. And it calls the SMB interpreter with something akin to a pointer to the beginning of that portion of the packet. It says, you know what this stuff is? Or otherwise, demultiplexes it. And then a program runs and decodes what fields it wants, writes data to virtual windows in the system, which, as you'll see in a moment, can be scrolled and zoomed and printed and saved to disk. And all that mechanism is done by the system. All you have to do is write a little routine which decodes the few bytes that you want. And if, for example, if someone decided that DG were to be sending SNA frames over ISO transport, okay? The other possibility is to take existing bits and pieces of the system that we have, such as the SNA decoder, and basically call it from some other path. So we have people, for example, who are running SNA over XNS. It's not a commercially available type product. That's what they happen to have in their situation. They can take basically an XNS interpreter that we have, and an SNA interpreter that we have. So you glue them together, and you get some other stack. And those stacks then are what we call protocol suites. Protocol suites are just, selection, one from column A, one from column B, one from column C, of all these different protocols that call each other. PCI is one of the stacks. XTS would be another one. COWS, lives off here, and so on. They can all be put together on the same machine. So that's sort of the concept of what's going on. The other concept then is the issue that there are two ways generally to address an entity. There's its physical address, and then there's its high-level address, we call it. Okay, for example, at the network layer, whether it's IP or ISO network, it has its own unique address that's specified that can be used to route those packets around the world. Okay, so now let's put all this together and take a look here. Okay, I just loaded some data. It was a file we had before, and I made a couple changes to some display filters just so we can see something clear. I'll go over now to my display filters. And I told it that I would like to look only at SMB type messages. Okay? The intent here, by turning off other options, is exactly what I said. I just want to see a slice of the system. I just want to see the SMB level talking to itself. The other acknowledgements, the other acts, transport, no. I just want to see only those packets that have the SMB level, and I only want to see the contents of that particular portion of the packet displayed to me. And the other thing that we did was we were just focusing now on two stations, Bob and Harry here, one's a server, one's a workstation, and I just want to see SMBs going back and forth between those two guys. Okay. And up here, just point out there's only one check mark on, which has to do with what kind of windows are being displayed. The one that's on is a summary window. So let's go look. We have three buttons which will display things, and we'll open up the summary window. Labeled here, and typically it has delta time in this column, the destination of the packet here, the source of the packet here, and some very brief message about the contents of that packet in the right-hand part here. So packet number 1 was from Harry to Bob. It was an SMB command that said search in the directory UDD, subdirectory Marriott, for question mark, question mark, question mark, question mark. I might have to scroll and hit the right arrow key. It actually was some stuff off the right of the screen. Just scroll sideways, scroll back and left. Okay? And then down here, move the down arrow key, our cursor moves to this next packet, which is from Bob to Harry, and that's an SMB message, and that's a response type message. Okay? And he says, what issue was found? So obviously, there was a file apparently in that directory, so many of these match up. And this word done here indicates that although there's no point going back and searching for any more entries. If there was one entry, it searched the end of the directory, and it was finished. And how long did it take Bob to respond to this query? The answer lies over here. It took 0.051110,000. It's 51 milliseconds to do that. Notice, by the way, there was some other packet number 2 here. You have to notice those numbers, which are the frame number or packet number, are not sequential here. 1, 3, 5, 9, 11, 12. There are 2 reasons why this frame number should have been skipped. One reason is we only wanted to see traffic from Harry and Bob. Notice that was here. The other reason was we only wanted to see frames that had SMBs. So there could be all kinds of acknowledgements and this, that, and the other thing. CEO, WS packets, whatever. It didn't happen to have this protocol, and the system took them out of view. They're still there, still in the buffer. And now we can get some idea of what's going on. I'll make one more change to the display to make it even easier to follow. I'll press F6, my display options. And over here, I have the ability to put it in a 2-station format, where when I'm looking at a dialogue between 2 particular stations, it has the effect of staggering the messages left, right, left, right, left, right. The messages from Harry here, and the messages from Bob there. We can now see the sequence of communication between those messages. Okay? Between those 2 stations. This helps our eye follow what's going down. So notice the directory search, other directory search. Interesting, these look the same, right? And yet here it said 1 entry found, 8 entries found. And we'll see in a moment what that's all about. Check some directory, continue searching, find out about a disk, open a file, the file was open, read some data, the data was read, close the file, reopen the file. Okay, so we need some idea of what this application was doing. At this level, we can only see a pretty high-level view of what's happening. Let's go down and look at the same network. Let's look at ISO transport. Okay, take exactly the same data. Go down to my filters. And this time, I'm going to tell it over to my protocol filters. And instead of turning on SMBs, let's turn on ISO transport. I'll turn on SMB. Press F3. Okay, And now, in fact, here happens to be packet 1, 2, 3, 4, 6, 9, 10. All right? And what happened here? Packet 1 was from Harry, an ISO transport data packet, destination 0005, sequence number, sending sequence number 67. Okay? And we'll pick up these little verbs named. They're generally industry, taken from various kinds of industry type notation. And here is an acknowledgement. Packet number 2 is an acknowledgement back to destination entity 2603, saying that I'm now ready. The next received sequence number is 68, implicitly accepting 67. And then he sends packet 67, his number 67, this guy, he acknowledges it. He sends 68, he acknowledges it. And whatever. Let's go back.
Here's a question.
Yeah.
How do you know if the packet contains SMB data?
How does the sniffer figure that out?
Yeah.
It basically decides that based on certain data, in this case, that's present in packets. It's a certain kilobyte sequence that it uses to do that.
Suppose we want to do a protocol that doesn't have a unique pattern at the beginning of every packet or something.
That is in general a typical problem. And basically what you need to do is to think about the question, well, how do the object, the entities that I'm looking at decide what it is that they're communicating?
Yeah, at the high level of like the session layer, you have a session between the server and the client. Once you get the session, that's all the only kind of packet you go back to. Once you don't really care.
That's right. What we have done, there are some other protocols which, in fact, you cannot tell by looking at the data what protocol is running. It's not contained in individual packets. They use that information when they set up the connection. And to do that, your protocol interpreter has to actually look for, in its interpretation, session type connections. It has to know about the sequencing and follow that through the link IDs and the other stuff and go on. And we have to do that for some protocols. That's considerably more work than just encoding a packet on the basis of the content it has.
So it's more
Protocol interpreters can do that.
It's more work to write, but don't you get in trouble trying to do that in real time as far as speed?
We're not looking at real time. In fact, we're looking at buffer.
Well, didn't you ask to only capture SMB packets?
No. It's going to display. Okay. That's an example of the difference between what it can do at display time and what it can do at runtime. At runtime, you can tell it, for example, which SAT to collect, because that's a fixed quantity, a known quantity. You can tell it at runtime, capture time, which, let's say, ether type, if it's an ether network, and we'll do that filtering. Finding anything above the hardware addresses and the simple hex offset will involve arbitrarily complicated calculations, following protocols, and it definitely does not do that kind of thing. And that's why, for instance, the filter, the initial hex filter, is just an offset. Now, generally speaking, you can, by examination, decide, aha, this protocol always starts at offset 22 in a certain field. That's more empirical than absolutely true in all circumstances. It works in practice. So here we're looking at that. We might want to do things like say, how long was this file open for? I'd like to know how long was it between this file open and that file open. And one way to do that is I can go down, I can change the display. I'm changing the notation that's used in the summary window. I'll go over and use other options here. I can indicate, for example, the relative time between two events. So I press spacebar, back to my display. Now if I hit function key 2, set mark, it marks this frame with t equals 0, and at all times are measured from this frame forward and back. So I can just read off, okay, this file is open for 0.78 seconds. I want to see how slow a server was in responding, how long it was between acknowledgments. This is another technique you use to figure out how long it's been acknowledged. Okay, let me open another window. We have up to 3 windows open. The one we're looking at is a summary window. You can also have a detail window open. At the detail window, shows us for each frame a lot more information. Now let me go back to the beginning of the session here. I hit home. This was a search, which returned one entry. And notice this search, so it looks the same, returned 8 entries. But obviously something different about those particular messages. This window down here is giving a lot more information than we see up here about that particular protocol. Search directory command, function, all kinds of other parameters, file name, whatever. And as I scroll to the top window, it updates the bottom window. Okay, corresponding. Let's go back to the first one. And I'd now like to scroll this window. Actually, use the tab key, moves the cursor between windows. And I can scroll around. And find out that that particular search command had some bit on, which apparently means it was searching for a volume label. Okay, I don't have the foggiest idea of, why that bit means volume label. I would never know. It's buried in some obscure document. But that was something we needed to know. Basically, the sniffer do that, answer the question, and we can see that that was looking for a volume label. I press function key 7 next frame, function key 8 next frame. So now in this frame, one entry was found, and here is the name of the volume label that came back from the server. Was this MV2B, some bytes, some timestamp. It was created in 1996, nothing like being ahead of its time. See, that was a perfectly legal, timestamp. It's just ahead of its time. And the system didn't object to it. It was an illegal one, it would put up question marks and all kinds of stuff. So now let's do next, function key 8. We're looking at this search command here. And down here, what's different about that? It's looking for directories. It's not looking for volume labels. It's looking for any directories. And normal files will be listed, not system files, not hidden files, and read-only files will not be shown in this directory search request. If I go to the next frame, now here I see, and again, the entries returned by the system. These are the names of the files in that directory that was being searched that met that criterion, and here is the information encoded. Right, obvious. Let's take a look and see what the information looks like. We open a third window, which is a hex window. Now this hex window, that's really big. That's all the sniffer collected. That's all the sniffer knows about. This was this packet. Okay? Here, my cursor is on this line that says search directory response. These bytes down here that are highlighted are the bytes that are the SMB level information. Okay, there's some stuff above it, perhaps some stuff below it. If I go down, look at the function code, 81 search directory, that's this byte. So now, can anyone tell me if I wanted to connect the sniffer to a network and only collect, I think there's a problem with directory searches on a certain server, how would I set up a filter to collect only examples of directory searches to a particular server? Hex value, that's right. You know all that is amazing. You ever heard that 81 after hex position 53 is search directory. If you forgot, you could just check it. If you knew, but you weren't sure you knew, so you can use this. I look at one example, you can figure it out. Okay, so you go to your capture filters, you say, okay, I want to look at packets where I have function code 81 and offset 53, and by the way, only 2, server bread, whatever. So I think I have a problem there, and I only see that set of packets. Now there may be other packets that have this function code at that offset. Okay. In which case we might get more than we need. We might do a better job. It just so happens, if you notice here, accidentally, the letters SMB are part of an SMB packet. That's how we know it's an SMB. So in fact, I could make a sharper filter by looking for a hex 4281 at that offset. That's less likely to get fooled than a random 5. Okay. In any case, you'll get at least the data you want. You make it more of the data you want, and then ways to filter. And basically, as you go through the information here, it shows you where it comes from. So, for instance, let's say someone was concerned. Let's go back, right, to this timestamp. Oops. That was so unusual before. And here we are. This is the search directory response that has this curious timestamp. It's not inconceivable that some software might have a problem if it ever got that data. It might do some funny thing. This line of information was decoded from this field. And somehow this field is supposed to be these bits of name, number bytes, and the timestamp. That was probably to send this off to the appropriate person to look at. And some user said, this is wrong. This is the wrong timestamp. How come it's on my display? So this is ridiculous. You could use this to look at the packet and say, surely the problem is not on your workstation. This is not a dashboard problem. It's not a workstation problem. That was, in fact, just 1996 or 1896. I don't know how it's interpreted. 1996. That was what the server said. So if there is a problem, if we're going to fix anything, we better go look at that server. Okay? Because it's not your display. It's more crazy. It's not your word processor's fault. When the word processor goes out to lunch, maybe the answer is, aha, we went out to lunch because it can't handle data that big, whatever the stereo would be. But it's telling you what's going on. Let me press function key 4. Press function key 4. In general, that will zoom windows up to full size. And now I'm going to scroll the screen upwards. Okay, so what we think is above the end of the screen before the SMBs are the other levels of protocol. Okay, that were carrying the SMB information. That was being handled by ISO transport. Here is then a full decode of all the various fields. There was some bit fields. This was an end of data. Bit was on in that particular ISO transport. That was being carried by ISO networking information, a lot more options, lifetime of packets, whether or not it can be segmented, all kinds of things potentially might be relevant to solving problems with data forms, gateways, and so on. That is being carried by logical link control, 802.2, these particular service access points, or ISO service access point. And then finally get down to the Ethernet. Okay, this is basically the Ethernet, the data link information. This frame was for Harry from Bob, and then its length was 148 bytes. Okay, so all different levels of the protocol are being decoded in this particular window. So these are 3 ways to look at data: detail where it knows it, summary to get a high-level view, hex for things that we otherwise don't know, user data, what was in a file, and so on. So one more thing that I'd like to show, then I think we'll break and go through that. And that's the following. Notice here, the source and destination addresses are Harry and Bob server. And as we said earlier, those might be gateways. There might be many messages, in principle, flowing between Harry and Bob, none of which are actually from Harry or to Bob. Those could be the names of just some kind of gateway boxes or backbones. If that's true, the actual names are in these fields: the network layer, destination address, and source address. Okay. And data general includes them as follows: with some letter P and some string. Okay, in them. Now, let's do the following thing. Let me go back, turn off some of these little windows here. Let's turn off our filters. That's why we get a lot of stuff on the screen. Address number. Message back to Bob server. Back to that. Okay. Let me do the following thing now. Let me go and turn off this two-station mode, and tell it that I'd like to show information not at using the data link addresses, okay? But I'd like to only see packets that have ISO addresses. Okay, we should frames with ISO address field to display. Yes. Now if I go back to my display, here it's showing me the actual ISO address, okay, and it's found in the packets. Okay. So I might not have known at all who the names of these stations were, what the servers were, carrying my ISO information. I can use that. Now, for example, what we were looking at before was, sys03 talking to MV2B. We could pick some other thing here. Okay, we can look at PC1. Okay, let's see who PC1 is talking to. Now, for example, if I go to my filters, and select station. I pick that back. Now it's showing me only traffic from this station. In this case, you have to talk to two different servers here. The filtering is now done based on the true source of destination. TCP IP and ISO, that's a very convenient way to do it. The hardware addresses may not be meaningful. You can have a table of this information, you can keep it on the disk in various places you can generate it. General mapping between names and addresses, whether it's an IP address or a hardware address, is done by table lookup. And those tables you can edit manually or they're kept in a very, very simple ASCII form. Describe it manually, you can just type out one of the files to see it. You may wish to maintain that using a database or some other machine, things like that. Rename that table. Yeah, multiple tables. And you can have multiple tables and look things up in those multiple tables, basically. That operation here, essentially, this menu, edit names, I go and manually update, delete, add names, okay? I can clear names. Loop for names is really not very, it doesn't mean anything in the case of ISO protocols right now. Like the future. Resolve names is basically a way of telling the system to use some other names file that's on the disk to look things up in. So basically, they have a series of addresses, you wonder what the names are, and then you tell it to use this file, which might be per site or per customer, or you can actually do a DOS rename before you start the snippet. A little batch file, you can rename it for each customer or each something. Okay. So here was we were talking before about heartbeats and stuff like that. It shows it, but it gets some sounds and that kind of stuff. If you like, you can actually do the best thing. You can stop now, ask me questions, and then try some of these things in the lab, look for this stuff, we can generate, suggest the kind of things you want to do are, one, just get familiar with the system. You'll have chances to do that as well with the demo disk. Play around with menus and so on, will give you some help. Just take a look at what kind of displays you see, how you can change them, how you can only look at traffic between everything on the network or just two particular stations. Try and look at some DOS traffic and see if it makes any sense. We have some programs there that are just constantly running, doing directory lists of the machines, stuff like that. You can see sort of what that kind of stuff looks like. You can bring up some CEO, WS stuff, and you can see what that looks like, and what level of information is there, isn't there. Stuff like that. And try doing some filtering. Try setting up something that would say, gee, I only want to look at file opens, or I only want to look at directory searches with more than 8 entries, something like that. Now 2 o'clock. Why don't we get back here? We spend about an hour go up for an hour and talk on desktop systems. This is really a continuation of that problem. Never marketed. Yes, realistically specs, on one hand, what's so incredible about these networks are that every day there's a new problem. You've never seen it before. The variety of ways that these systems can get into trouble is just boundless. On the other hand, a lot of experience that we have shows that most of the problems, though, are really very straightforward and pretty prototypical, and you can handle 99% of the problems or 80% of the problems fairly straightforwardly. Good old cabling and wiring is a classic example of that. Everyone believes that he can make a cable. I mean, that's what the whole message of the industry is, and all the Starland stuff and everything. I mean, you just go out to the store and buy it, you have pliers, and you build your own cable, right? You can do that. Turns out that the quality of my crims is terrible, and they have the sad problem of almost working. Okay, if they work at all, really, but they sometimes work. And the classic problem of intermittent cable, of something that's marginal, is a classic thing. It's very hard to find, very hard to localize. It has all kinds of bizarre effects that you can never pin down. And I think there's a lot that's going to go into just realistically checking out the cabling. Now, a good way to do that often can be to look at a screen to see what stations are on the network, where they are. You have some idea of a map of where stations are physically. In the topological sense, you have a pretty good idea of what's happening. I would recommend that as something that ought to be taken fairly seriously. Efforts been made to really track where stations are topologically, what their addresses are, what their symbolic names are. So when you do go into a problem situation, you have to start from ground zero, 150 workstations on a network, all with hex addresses, and all kinds of other bizarre stuff. No one likes to do those things until they have to do it, but it's probably a good investment if people get around to doing that, keeping track of which stations are where in the network. So you can just make a quick judgment. You see station A, B, C, D, E, you don't see station F. Aha, there must be a problem somewhere in that part of the building. And these would be really valuable things to do. They're hard to keep up to date. It's the kind of thing, certainly, I think, as a service offering or something else, if the people who are doing the service appreciate the reason for it, they can go in and do it on a quarterly basis, monthly basis, and obviously attend the installation, and try and keep that information up to date. The other issue that happens a lot is what we refer to here as logical flaws. In other words, nothing is broken. The system is working. It's just that it's not doing what people think it should do. Everything from a lack of familiarity. People expect it should boot this way. They type a certain command in, they don't get the right result. People, I think, will spend a lot of time believing they're using the system correctly, thinking they're typing the right command, thinking they're accessing the right thing. And that's just not the way it works. That's just not the way it's designed to do. And there can be a lot of mysteries from simply typing the wrong parameter. Jobs get lost, printouts don't happen, files disappear into the wrong subdirectories. And we need to track these things down by showing that, well, yes, something happened, but that's not what you thought. By looking with a tool that's on the network, it has the advantage of being sort of a neutral third party. It's not the workstation, it's not the server. You can see things so uncluttered. You don't have to add debugging tools and get confused with either of the two parties in this conversation. You can sit in the middle and sort of clearly see what the hell's happening, and generally in a matter of seconds figure out, aha, you put in the wrong subdirectory, you are creating that file, that's where it is. And the problem is over with in a matter of seconds. Typos, people setting wrong parameters, setting 7-bit mode instead of 8-bit mode in terminal emulators, not putting character terms after line feeds, all that kind of stuff falls in that area. Another real problem from a performance point of view is programs written by customers. And that would be everything from the kind of things we talked about, like just search order. Okay, how do you find a file? We can do it very inefficiently. Going out and buying a database program that works very fine all the time. We might be maintaining a mailing list with this program, and a very acceptable way to keep track of things. And once a week, we go and update that mailing list, add a few names, sort it, print out a new version, and so on. It takes 10 minutes. And one particular week, the person goes in, adds some names just like the week before, starts the sort going, goes out for a cup of coffee, comes back 15 minutes later, it's working along, it's not finished yet, goes out and has another cup of coffee. Meanwhile, everyone else in the building is going crazy because their job isn't getting done, nothing's happening. And this could be accounted for by that particular program just hit some curious threshold, adding 2 more records to the database, caused it to go into some incredible thrashing mode, where it's swapping over the network, reading and writing to the file server, just doing things very, very inefficiently, just because he did exactly what he was supposed to do. He added a few more records to the database. And that particular example was one that we spent a lot of time, once upon a time, working with customers that could not understand why a certain application was running so slowly. It had to do with very strange behavior of a certain database package and multi-use database package. Once it hit a threshold of a certain number of file entries, it switched to a different algorithm. And just its behavior was radically different than it was a couple days before. There's nothing in these systems that prevent you from making rather abusive use of the system with very high efficiency. You can write an excellent tuned program that works very efficiently and just read the same record over and over again. Okay, 1,000 times over instead of buffering it or caching it. It might be that the server is real generous when it finds that your request comes in and you want to read a record that already has in its buffer. It locks that one into memory and gives you a nice high priority and says, gee whiz, don't go on this for this guy. And all the other guys sort of fall behind in the queue, and this one user ends up chewing up 90% or the lion's share of the CPU attention of the server because he happened to be reading the same record over and over again, and everyone else in response just goes to hell. Terrible. And again, when we say it's customer code, it's not customer code like the old day where someone actually sits down and writes about a bit of program. They bought a package, or it's a word processing package, or some application code he's running. It's a well-known application from a famous vendor. It would happen to be wrong. It used to always work, and now suddenly it's not working. Or he was using it on his PC network, and now it's on his server. There seems to be a logical reason, but very often it's no one around, certainly not PG, not the service people, not the customer, really knows what this application is doing at a detail level. But I think you get some feeling by looking at these SMBs, you can spot obnoxious programs pretty quickly, and at least know that you've got to talk to the application vendor. Very often what happens then, he says, I'm not doing that, I've got to talk to the guy who wrote the compiler. And the guy who wrote the compiler, he's got to call some other company that wrote the runtime library, which is really doing I/O, that's really causing the problem, and you can pass on the change 7 levels. But at least you got someone looking at the problem. And you just go and start swapping boards and changing cables and changing parameters of the server, it's just never going to fix it. They feel better, the customer may feel better, but it's not getting any closer to the solution yet. That's the thing to do while the other guys are trying to find the guy who wrote the runtime library. And that's a very common phenomenon. This gross inefficiency in places that people aren't aware of can show up real quick. And, there are occasionally bugs. I've been told that every now and then it might be incompatibility. Indeed, it's true that, for instance, the MD server is an implementation of the DOS SMDs for a certain spec. You can be sure that there's going to be some case someday or some particular version of an SMD that gets interpreted by the server that's not exactly the way the workstation expects it. It may be exactly the way Microsoft wrote their spec. It may not be the way the code that's running on PC expects it. And it's going to get mighty upset. And it's not a question of who's right and who's wrong. It's a question of finding that particular example and getting someone looking at it and making a little bit changes so that option of that command that day of the week works reasonably. I think in the next 6 months to a year, all that category of bugs, features, whatever, implementation details that have to get resolved. And that's why having a very technical tool will help. And those problems tend to be very, very mysterious ones, and ones where you can quickly get a bad reputation for not being compatible. People really expect it to be bad. The other kind of problems people have are connectivity. A classic case I saw somewhere users are really good, end users, hey Joe, I've got this great new package here, oh wonderful, let me try it, sure, copies the scan, and he takes the scan, puts it in his machine, and boots it. And things might happen like two stations trying to get the network both using the same name. Okay, the same IP name or something like that. A little thing, a little innocent act by two users booting from the same boot diskette in certain software in certain environments can cause incredible havoc for everyone else. All kinds of things happen. Systems get very confused. They find two different stations that have the same name but physical address nowhere. Tracking those things down becomes rather easy to detect when you can see what's going on, when you don't look for, and those are going to happen. Lots of other things, bad paths in the system. Initially, I imagine many systems would be simple. They'll have just one server or one subnetwork. And as that grows, and you have more networks that are interconnected together, X25 stuff between them, room for complications grows. TCP/IP, that's standard. Almost everyone's system has multiple gateways and routers and bridges. Certainly, large Ethernet systems. Most Ethernet systems today, they're not in truly small shops. They're all to be quite significant. Where they have virtually hundreds of PCs, gateways, bridges, subnet routers, fiber optic links, broadband links, you name it, they got it. And it's a complex system, but very manageable with the right tools, the right techniques to look at. It becomes pretty straightforward to do. That's the kind of things, again, an expert can look at, remotely, dial in, and literally in a matter of hours solve the problem. We've seen lots of situations with some kind of looping going on in the network. Data gets routed around, comes back, the same guy. A really well-tuned system is great. Because a well-tuned system, everyone gets a packet, immediately passes it on to the next guy. He immediately passes it on, let's say, back to the first guy. Then he passes it on to the next guy. The net effect is the system appears to run slowly. Now, the gateways are locked down. And every attempt you make to tune them and make them faster, of course, only slows them down even more because they're just more efficient at doing the wrong thing. So and it's very hard to detect that kind of stuff without actually having internal counters and internal traps. It's not a problem. Most people's complaints fall in very generic categories. Three of them are performance, and performance. It's like going to a doctor. You go to the doctor, and everybody says the same thing. I don't feel well, it hurts, it bothers me over here. All symptoms sound alike. The same thing is true with these networks. All the calls in to field service are all going to sound exactly the same. It's too slow. I can't log on. I can't move. That's all it's wrong. It's too slow is a big one, and that happens again because of the fact that people are really misusing the system inadvertently, advertently. They're playing games on the network, sorting things over the network, whatever it would be, without realizing that they're impacting other people's work. There's nothing in these servers generally that limits people from doing that. Okay, they generally are first come, first serve. They optimize their own workload. They don't do load sharing or load balancing or anything like that. It's first come, first serve. The model of these networks generally is you have a lot more resources than you ever need. The real world is you never have as much resources as you need. And a 10 megabit network eventually gets full. 1 megabit network gets very full very fast. The other thing are simply bad choices of parameters. You have lots of things that you can set. Packet sizes, timeouts. What timeout should I use? Occasionally a packet will get lost. Retry is necessary. Should I use a 1 second timeout or 7 second timeout? The predicament is almost all systems today give you a choice of a number. You can pick it, but it's not to be sensitive to load. So that you're faced with all the predicament that if you tune it for a less load system, you might want to have those low-level timeouts and quickly retry and give you a flop. The system gets very loaded, you're going to have huge amounts of unnecessary timeouts because things are just queued up. and it would take longer periods of time. You set your timeouts high, as a standard, then you ship it to someone who is using it lightly, and every now and then he's got this incredible long, 15-second timeout or 5-second timeout instead of 100 millisecond timeout, and long periods of idle time go by with no activity. So how do you know what to do? Well, I think you have to go in, look at the system, and adjust it, potentially adjust the timeout size, adjust the parameter. Questions of how much CPU time you give to server process versus backup processes. There's no magic to that. It depends on the customer and what he wants to do. All Sniffer is going to do is, in the old days, is help find out what's wrong or what's not wrong. I think you really think about it from that point of view. When you used to go to a doctor in the old days, say it hurts over here, he look at you, he's an excellent doctor, the best diagnostician in town, ask you a few questions, stick out your tongue, put a tongue compressor on and say, aha, take 2 aspirins, call in the morning, you'll be fine. And he was a good doctor, that was probably a good recommendation. If you came back the next day and said, no, it still hurts over here now, you might say, well, take some antibiotics, wait 2 weeks, problem's closed, gone away, you try something else, and eventually you find out what's wrong. You're in pain, for a couple of weeks at a time, but eventually found the problem. He's a good doctor. He used the right judgment, right medical decisions as to what steps to try. That's a very effective way and a very possible way to deal with a lot of network problems. You can go about it very systematically using that kind of judgment. Aha, I know what that problem sounds like. You say you can't connect the server. We had that happen. This other customer right in the other city here. It was bad ROMs, bad version of software. Let's upgrade the software. On the server, you upgrade the software. The server, you wait a few days. The problem's still there. Thinks about it some more. Oh yes, we heard about that problem. You must have a bad microcode. You got to change the microcode. Change the microcode, all the boards, upgrade all the boards. And so on and so on. Eventually, you find out what the problem really was. The trial and error, process of elimination, you find the problem. But you've spent a huge amount of time trying things that just weren't helping at all. And what we'd like to see the Sniffer do in the field is to help people at least decide what's not the problem. Don't spend a lot of time, don't spend a lot of money, don't have a big fire drill over things that are not going to help the problem. And if you can just use it like as a way of seeing what's going on in the network. So it's like an X-ray machine. Look at, if something bothers you, take an X-ray and say, oh look, you have a broken bone. Okay, now the doctor, not the diagnostician, has to go and find a surgeon to do the surgery and fix your bone, let's say, or put a cast on or something like that. Well, Sniffer will help see what's going on in the network. We'll do it very quickly, like an X-ray machine. I don't know anything about medicine, I don't know anything about anatomy, but I can look at an X-ray and say, oh, there's a bone, there's a rib cage, and so on. So I guess the thought is that people in the field who are trained, supporting PCI and supporting other products, will be able to get that level of expertise. They can say, aha, that looks like the problem I heard about. It really looks like your timeouts are set badly. And then it's going to take someone else to maybe go in and know, how do you adjust it? What is the patch? What is the option? Do you recommend a new version of software? Or what you actually do may not be something that lower level service person can't handle. Very quickly get someone looking at the situation and decide that there is a fix available or there is some kind of support available. And that support can be called literally on the spot. I guess the biggest thing to keep in mind is don't jump to conclusions. Keep an open mind about what's happening. You can't assume a hell of a lot. People just give you very bad information. They don't really know what the state of their cables are, their transceivers and software, and it's easy to get low to the wrong thing. But People have a tendency sometimes to look for very complicated solutions to when there are really very easy answers. And most problems are really easy problems. There's just not going to be a lot of complicated problems. Unfortunately, when you run out of easy answers, and in the cases where it's not one of the simple things, it's a bitch. Okay? Problems fall in only two categories: really easy ones and killers. And very quickly, once it's escalated beyond the level of looking for the obvious 6 or 10 things that are wrong, it takes someone who's really clever and careful. And I think right now with today's technology, once you get out of the domain of easy solutions, you can't just go through a simple decision tree. There's just a million things that can be wrong, and you're not going to find the answer just by following check this list on the top ones, because there are literally thousands, millions, tens of thousands of possible things that could be problems once you get beyond the straightforward thing. And that's going to be the responsibility of higher level support. In general, there is a systematic way of finding out what's going on. That's the kind of thing that can be done easily on the spot. Go out, look at the entire network like we did earlier, look at just the servers, look at one particular server, one particular client, look at a certain protocol, and very quickly focus in on the problem, see if it's an endemic problem of the whole network, if it's a problem of just one particular server, if it's a problem just between one particular station and one particular server, and at least focus in and filter down on the customer side to find out the problem. The other, corollary to all this is that it's very difficult to reproduce some of these problems without the customer's data, the customer's configuration, the customer's network. So you have to go in and collect the data right there, and that's going to be the information necessary to suggest what should be fixed, what should be changed, what should be improved. And you can collect lots of data in order to then filter it down, but you can't just sit there and collect data all week. You cannot collect 100 megabytes of data, let the thing run for 24 hours, and then hightail it back to Wally or something and expect to think about it later. You have to actually have an attitude, which I find is non-traditional in most network communications approaches. Most people are used to wide area networks, an approach where you're typically looking at fairly slow lines to turn on something, collect massive amounts of data, where massive means hours or days worth, which is only a few hundred kilobytes, and then vanish. Think about it. That's not going to work with a local area network. In a local area network, you're going to have 10 megabytes of data before you're done having a cup. So a person in the field, somehow has got to be a little bit more discriminant than just going in, turning it on, collecting the data, thinking that the job is done. So that can be done remotely, perhaps, by someone else who's going to do that filtering, whatever the strategy is. But you've got to really get on with things that day, that afternoon, with the machine. All right. We only spent a couple hours here looking at the sniffer. You only spent an hour hands-on with it. I don't think I dare give you a test on your mastery of it, but I do think you might have a perception that it's not all that complicated. And basically, there are two principles to it: how you move around the menus, what you can do, what you can't do. There are lots of combinations and permutations, but basically, it's laid out fairly straightforwardly. Given a couple hours of practice with the demo disk or with the live system, you can feel pretty comfortable about it. And more than that, you will feel comfortable enough about it that even if it's not your day in and day out tool, it's something you only have to use once a month or once in 6 months, and you can go back, pick it up pretty rapidly, and get back to doing some useful work without it being a full-time occupation. None of us know just how well these networks can work in practice, and what the frequency of problems are, and is this something that a tech specialist is going to do once a week, 8 hours a day, nonstop? We don't know. We just don't know how that's going to evolve over time. But I think it's the kind of thing that someone doesn't have to make a full-time career out of it, and you don't have to have one person in the corporation who's the expert. People can use it occasionally and get used to work at it. I think that in general, the kinds of problems it solves, the kind of tools it gives are far beyond what you normally need. Most of the information that you need can be very quickly gotten from some of the displays and some of the very high-level summary views. Exact details of bits and bytes and so on rarely is useful, certainly not in the field situation. It's there. It may be useful in a particular situation. It may be useful to set up a filter and other things on the spot. Think of it as a kind of encyclopedia. You store everything that you don't need except the few pages you need. It's really nice to know you have it. And literally, if you have to carry around books, reference books that describe the information in those, they are monumental tomes. I think the good thing is that it's straightforward enough that you can actually have customers, field people, developers, outside vendors, all looking at the same information and nodding their heads at the same time, and avoid finger pointing and usually some of the other problems that happen when you don't have hard facts. So, well, it must be your station. It used to work until we turn on that. Obviously, that kind of logic that says, last man in. He obviously broke the system. You can go in and say, no, that bug has always been there. Here's what's wrong. Your system is incorrectly broadcasted. You cannot send out garbage packets, that are broadcast packets with random data. You're crashing my server. Yes, I should be more defensive, but the problem is your code. And you get to the point where that's a semi-rational discussion. It's never possible to do those things. At least get the customer understanding why there's a problem when you tell them, look, I'm doing everything I can to fix the problem. That vendor's code over there really is the thing. If you can only call him up and get him to look at it and get all the things, and we can't really deal with that problem, that's the kind of very positive attitude you can take when you present information on a screen or printout. Now again, someone who's not an expert in protocols can look at it and say, oh yeah, I see that. It's reading the same record over and over again. Oh, look at that. I read that record and locked it, read this record, and then I read that record and didn't lock it. That's why I get bad information. They can understand that kind of explanation without being detailed protocol experts or network experts. Okay. I'm through with my spiel, and at this point, we're happy to have any discussions. If some of you have some specific questions about the protocols or what they do, or how you can extend them, I guess I asked you to start off by thinking a little bit about what you thought the sniffer might do and the problem that you're concerned about in your areas. If by now you're less than convinced or you think you need something else, I'll be happy to take some feedback or have a conversation about ways that we can help you more. I don't know if the answer is already asked.